Hi everybody. So this is your midterm review for nanoscience in spring 2023. I've got a lot to go through, so if I skip over some things that are written on the slides, forgive me, but the slides are here for you. The practice test will also be posted for you, and some of the questions on the practice test might look familiar when you take the midterm. Yeah, let's get started. So logistics-wise, of course, the test is going to be on Tuesday, March 7th at 3:30 p.m. in room 243. This is our regular lab time, so this will be in-person testing. You can bring in an 8.5 by 11 inch sheet of paper for your equation sheet or for notes. Please bring in a calculator, you'll need that, and you'll need some scratch paper too. Make sure that you write legibly because it's really hard to grade something that you can't read, and you're going to have to show your work, and if you show more work, of course, that can give more partial credit. If your answer doesn't have the right units or notation, points will be deducted for that. And the test will consist of some questions that are number crunchers and conceptual questions for this test. Okay, so launching into the material. This is nanoscience, right? So the nanometer is 10 to the minus 9 meters, or 1/billionth of a meter. And nanoscience is defined as research and technology development in the length scale of the 1 to 100 nanometer range to provide a fundamental understanding of phenomena and materials at the nanoscale and to create new structures, devices, and systems that have novel properties because of their small size. Nanotechnology is based on the manipulation, control, and integration of atoms and molecules to form materials, structures, components, devices, and systems at the nanoscale, and it is the application of nanoscience, especially to industrial and commercial objectives. It's important to understand that you can come at the discipline of nanoscience and nanotechnology from a number of different science backgrounds, and it's a very interdisciplinary field. So let's discuss some of the reasons that nanoscience is such an exciting field. One of them is that at the nanometer scale, properties become size dependent. And so you can have some nanomaterials that have very different properties from their bulk counterparts. One of them is that nanoscale materials have a tendency to be more chemically reactive than their bulk counterparts. And that's because, of course, their surface area to volume ratio. And we'll talk more about that later. Nanoscale materials also have different thermal properties than the bulk materials. So their melting temperature, for example, can be different. They have different optical properties. The color or transparency of nanoparticles are different than their bulk counterparts. And the electrical and magnetic properties are different for nanoscale materials. So exploiting these differences is the focus of nanotechnology. Nanotechnology has a long history, even if folks didn't understand what they were doing. The concept of the atom was developed in 400 BC, and in the 5th century, the Lycurgus cup had nanoparticles of silver, gold, and copper embedded in the glass, and that gave it its pretty colors and its interesting optical properties. In fact, people have been creating metal nanoparticles in stained glass windows in cathedrals in Europe for a long time as well. These date from the 6th to the 15th centuries, and they have these beautiful ceramic glazes in the Islamic world from the 9th to the 17th centuries that contain metal nanoparticles as well. Damascus sabers were really famous in the 18th century for being very strong and durable, and they, when you examine them using high-powered microscopes and different sort of analytical methods, have been shown to contain carbon nanotubes, which gives them their famous strength. And daguerreotypes in the 1800s used silver nanoparticles on the surface to give that black and white contrast, and there have been some really interesting papers on that. So this is all old technology that we now understand better from the perspective of nanoscience. So in the first couple of chapters of your nanoscience textbook, they talk a lot about the characteristic dimension, which is shown here as big D. And so this is just a metric that's used to simplify the size to a representative measurement for comparison purposes. So big D, even though it sounds like it should be a distance or a depth or something like that, can also be used for radii, the size of a cube, and things like that. So the square of the characteristic dimension will be proportional to the surface area, and the volume of the d cubed of the characteristic dimension will be proportional to the volume. So if you take the surface area to volume ratio, dividing the surface area by the volume, then it should scale as 1 over the characteristic dimension. Now, be careful, because on the test, if I ask you for what the surface area to volume ratio of a sphere is, for example, it's not just going to be 1 over r, okay? There's an actual formula for the volume of the sphere and an actual formula for the surface area of the sphere, and you should take those two things and divide them to get the exact dependence for this SA over V ratio if asked you on a test. It's not just going to be 1 over r, okay? You need to be able to calculate the formula. So as nanoparticles shrink because of this dependence on 1 over the characteristic dimension, as it shrinks, the number on the bottom for the characteristic dimension gets smaller and smaller, which means your surface area to volume ratio gets larger and larger. And this is huge for nanoparticles. And that's what really is at the root of many of the differences in nanoparticles and their bulk counterparts. Specifically, the enhanced chemical reactivity can be easily explained by this. So the surface atoms have actually fewer bonds than bulk atoms, and that makes their energies higher and makes them want to form bonds more than bulk atoms. Also, since the surface atoms are at the surface, it makes it more likely that they'll interact and encounter other atoms or molecules that come along because they're not buried. They're not at a buried interface. And so both of these ideas contribute to the enhanced chemical reactivity of nanoparticles. And we did a lab on that too. Okay, scaling laws. Some generalizations can be made for how material properties change as the characteristic dimension shrinks. And these are just proportionalities, and their accuracy will vary. But in Chapter 2 of your textbook, they discuss scaling laws for mechanical, electromagnetic, and thermal properties. And some of these break down completely in some materials, so be careful about that when you go out and try to do real research, to make sure that you truly understand specific examples when you need to. But make sure that you review the scaling laws for Chapter 2. This is just a list, kind of a laundry list, but I want you to look at all of them and review them. You're responsible for the basic physics behind all of these equations, which we covered in the online class in the scaling laws lectures. The level expected for your calculations is kind of like Modern Physics 1, which I'm sorry now is called Physics 2110. I'll never get used to that. So PHY 2110. It's going to take me forever because I taught that class forever, but there you go. Modern Physics 1. Okay, so here's a list of the scaling laws. Anything proportional to mass is proportional to the volume, which is proportional to the characteristic dimension cubed. Anything for the strength to weight ratio is going to be proportional to 1 over d. Anything proportional to wear is going to be proportional to d. Anything affected by friction is actually proportional to the contact area on the nanoscale. And the frequency of nanoscale oscillators, that's supposed to be NF, scales as d to the minus 3/2 power. Resistance, electrical resistance, scales as 1 over d. Current is proportional to d. Electric field is proportional to 1 over d. Electric power scales as d, and capacitance scales as d. So all of those things are scaling laws that you should review. Here's some more. The force of an electrostatic and magnetic actuator scales as d squared. Heat capacity scales as d cubed. Thermal conductivity scales as d. And the time to come to thermal equilibrium scales as d squared. The pressure gradient through a length of pipe scales as 1 over d squared. And the terminal velocity and the time to reach this velocity scale as d squared. The angle of diffraction scales as 1 over d, which is proportional to theta. And the resolving power scales as 1 over d for the lens, and the wavelength of the light or particle used for imaging. The focal length of a lens scales as d. So those are some of the scaling laws we covered. We talked a little bit briefly about microfluidics. Microfluidics is the study of the behavior and control of fluids at the submillimeter level. In microfluidic systems, the fluid flow is generally lamellar. Instead of turbulent and viscous capillary forces dominate the behavior of the fluid. Microfluidics exploits these differences for various applications, including inkjet printing and various lab-on-a-chip applications like blood analysis, among other things. For biology, we had some interesting scaling laws. We talked about how heart rate scales as mass to the minus 1/4 power, which scales as the characteristic dimension to the negative 3/4 power. And that means that if a type of animal is smaller than another type, its heart beats faster, which means that smaller animals live shorter lives. The lifespan is proportional to m to the 1/4, which scales as d to the 3/4. The metabolic rate also scales with their mass. Smaller animals are less efficient than bigger animals, so they have to eat more. So their metabolic rate, mr, is proportional to m to the 3/4 power, which is proportional to d to the 9/4 power. All right. We talked about different nanoscale fabrication techniques. And in sort of a big picture view, there's either top-down or bottom-up ways to produce nanoscale materials. So if you want to build the tiniest computer chip possible using the bottom-up approach, then you would use nanotechnology to assemble the chip atom by atom or molecule by molecule, placing each one in a specific location to build a circuit. But with a top-down approach, you would instead create the computer chip by carving away at a bulk material, kind of like a sculptor, okay? And by carving away, you would create nano-sized features, never dealing with the atomic level of matter. So that's kind of two approaches. One of the top-down approaches is photolithography, and that's exploited a lot in the semiconductor industry. So first you treat a substrate with a photoresist, usually by dissolving it in a solvent and spin coating it, and then you solidify the resist and evaporate the solvent, and then the wafer is usually baked. And then what they do is they use a stepper, and that's kind of shown here in this top picture, to shine UV light through a photomask, and that contains the pattern to be printed, and the lens focuses the pattern on the photoresist, which coats the surface of the substrate. The wafer is shifted or stepped so that an unexposed region of the photoresist moves under the optical system, exposing that region using UV light, and the stepping continues until the pattern is repeated across the whole wafer. Now, if you want to manufacture an integrated circuit, you've got to expose several different patterns on a wafer, and each of these patterns defines a particular layer or type of the material, and then you can stack them. Okay? So another method to create a nanoscale material. Anything that etches away or breaks apart a big material to make a smaller one is top-down. So there's lots of different methods for making nanoparticles, and some of them include milling, rolling, beating, microtoming, chemical etching, polishing, combustion, electrospinning, arc discharge, sonication, and extrusion, among a huge list. So all of those are top-down. Bottom-up methods of synthesis include some of the ones that we did in lab, chemical reactions in solution, right? So we made nanoparticles in the lab using chemical reactions in solution. Self-assembled monolayers, SAMs, chemical vapor deposition, CVD, and molecular beam epitaxy, MBE, are some of the bottom-up methods. Now, Chapter 3, if you remember, was a review of some of the undergrad material that you learn in Modern Physics 1. So some of those concepts, I'm just going to go over them briefly here, include the photoelectric effect, which is the idea that light shining on a metal surface can be used to create photoelectrons, which are then freed from the surface. The equation for that is HF is equal to K plus phi, where HF is the energy of the photon, the light that strikes the surface. K is the kinetic energy of the photoelectron that's released, and phi is what's known as the work function, which is the amount of energy that it takes to free the material from the substrate, free the electron from the substrate. We talked about blackbody radiation in Modern Physics 1. There's two equations for blackbody radiation that get covered a lot. Stefan's law on the left there and Wien's law on the right. Stefan's law is P is equal to sigma AE, T to the fourth minus T naught to the fourth. And that gives the power of a blackbody radiator. Sigma is a constant, 5.67 times 10 to the minus 8, so that's a constant. A is the surface area of your blackbody radiator. E is the emissivity of the material, which goes from 0 to 1. 0 is a perfect mirror or a reflector, and 1 is a perfect blackbody or absorber. T is the temperature of the object, and T naught is the temperature of the background. Because, of course, if the object is at the same temperature as the background, you're not going to get more power from the object than you do from the background. You have to have a temperature difference. The other one is Wien's law, shown on the right. Lambda max times T is equal to 2.898 times 10 to the minus 3 meters times Kelvin. Okay, that's not millikelvin, that's meters times Kelvin. So lambda max is the wavelength of the light emitted from a black body radiator at the peak of its intensity. Remember that the black body curve has that characteristic hump with that long tail on the right-hand side. So lambda max is the peak intensity wavelength, and T is the temperature of the black body radiator. So what this shows is that as the temperature of a black body radiator increases, the wavelength of its maximum intensity decreases. So you get shorter wavelengths with hotter objects. The next equation describes de Broglie matter waves. Okay, remember that everything exhibits wave-particle duality, and so small particles like electrons, protons, and neutrons, their wavelength is actually larger than the particle themselves, and so their wave nature tends to dominate, which is what causes basically all of quantum mechanics. The wavelength of a matter wave, lambda, is equal to h over p, where h is Planck's constant. H is 6.626 times 10 to the minus 34 joules seconds. By the way, on the test I would give you a table of fundamental constants, so you don't need to write that on your sheet or anything. And p is the momentum of the object. Now the momentum could either be relativistic or non-relativistic depending on how fast the object's going. Okay, but remember that classically p is equal to mv, where m is the mass and v is the velocity. And if it's traveling at relativistic speeds, then it's gamma mv, where gamma is that 1 over the square root of 1 minus v squared over c squared. It's the gamma factor from Modern Physics 1. Okay, next is the Heisenberg uncertainty principle. In one dimension, the momentum, position, Heisenberg uncertainty principle can be written as delta x delta p is greater than or equal to h bar over 2. Delta x is the uncertainty in the particle's position in the x direction. Delta p would be the uncertainty in the particle's momentum in the x direction. H bar is Planck's constant divided by 2 pi. And remember that the greater than or equal to comes from the fact that a Gaussian wave packet has the minimum possible uncertainty, which is equal to h bar over 2. And every other kind of wave packet is going to have greater than that uncertainty. Next, we covered the solution to the Schrödinger equation for the infinite square well. Remember that the infinite square well is the particle in a box, which means that there's a 100% probability that the particle is confined to the box. In other words, the probability is 0 that it's outside the box, which means the potential at the walls of the box is infinite. And this is the one-dimensional solution to that Schrödinger equation. It shows that the wave function psi of x is equal to the square root of 2 over L times the sine of n pi x over L. Here, L is the size of the box, okay? And n is the energy level, all right? Now, we did also spend time covering the structure of the hydrogen atom, the Pauli exclusion principle, and the structure of the periodic table from Modern 2. But this slide shows you the key concepts and takeaways that I want you to remember for nanoscience from Modern 1. Okay, so moving on to the Modern 2 material. The quantum numbers for the hydrogen atom, basically, if you solve the Schrödinger equation for the Coulomb potential, in other words, the attraction that a proton feels to an electron when the electron is confined to orbiting around that proton. You solve that Schrödinger equation and you get 3 principal quantum numbers out. Those quantum numbers are n, L, and m sub L. N is the principal quantum number, or the energy level. That value can start at 1 and go up in integer steps from there. The ground state is n equal to 1. L is the orbital quantum number. The orbital quantum number starts at 0 and goes up in integer steps to n minus 1. Okay? So there's going to be n allowed states. For example, if the particle is in the n equal to 3 energy level, then the orbital quantum numbers could be 0, 1, or 2. All right? And m sub L is the magnetic quantum number, and the value of L dictates the possible values of m sub L. So, for example, if a particle is in the L equal to 1 orbital, then the possible values of m sub L are 1, 0, and minus 1, because the orbital magnetic quantum numbers run from minus L to plus L in integer steps. Now remember that there's degeneracies here, okay? Degeneracy is when there's multiple states that have the same energy. So you can see here that there's going to be 2L plus 1 possible values of M sub L for every value of L, okay? And then there's going to be N possible values of L for a particular N value. All right, so the meaning of these quantum numbers, using the energy level or principal quantum number, you can calculate the energy of the electron in the hydrogen atom. So that equation is given by minus 13.6 electron volts divided by N squared. So something in the ground state where N is equal to 1 will have a binding energy. It will be bound by 13.6 EV. L dictates the angular momentum of the particle in its orbit around the proton. The value of L, the magnitude of that value, is equal to h bar times the square root of L times L plus 1. L sub z, or the z component of the angular momentum, can be calculated from M sub L. So M sub L is times h bar gives you Lz. Remember that you can't know explicitly Lz, Lx, and Ly all at the same time because that would violate the Heisenberg uncertainty principle. So there's some notation that's left over from spectroscopy and chemistry that we use oftentimes to talk about shell and subshells in the hydrogen atom and in atoms. So for example, we call the N equal to 1 the K shell. We call the N equal to 2 the L shell, and so on and so forth as shown in the table. In chemistry, you might have seen the notation for subshells, if you took that. L equal to 0, 1, 2, or 3 are the S, P, D, and F orbitals, and you're probably relatively familiar with those, I hope. Now, solving the Schrödinger equation will only give you 3 quantum numbers, but there is a 4th fundamental quantum number that you get from relativistic quantum mechanics, and this one is electron spin. Spin is an intrinsic angular momentum that particles have, all right? So, for example, for electrons, protons, and neutrons, those are all fermions, okay? And they have, therefore, half-integer spin. There's 2 direction for spins for electrons, protons, and neutrons. And we usually call those 2 directions spin up and spin down. And what this means is that in the presence of an external magnetic field, the energy of the electron is slightly different for the 2 spin directions, and it produces doublets in the spectra of certain gases. So, for example, if something is spin up versus spin down, then it will either, the z component of that spin angular momentum will either align or be anti-parallel to that external magnetic field. Okay? So that corresponds to magnetic spin quantum numbers of plus 1/2 for the spin up case and minus 1/2 for the spin down case. Okay? Spin up is generally considered to be aligned with the field and will be the lower energy state in the presence of an external magnetic field. We covered the Pauli exclusion principle. The 4 quantum numbers, N, L, M sub L, and M sub S, those discussed so far can be used to describe all of the electronic states of an atom, regardless of the number of electrons in its structure. So even though the solution to the Schrödinger equation is not exact for multi-electron atoms, it still follows the same patterns and has the same quantum numbers, all right? The Pauli exclusion principle states that no 2 electrons can ever be in exactly the same quantum state in the same atom. So no 2 electrons in the same atom can have the exact same state of quantum numbers. If the exclusion principle was not valid, then an atom could radiate energy away until every single electron was in that lowest possible energy state, which would be the 1s state, or the K shell in the L is equal to 0 orbital, okay? And that would completely change the chemistry of everything that we know. That is not how matter behaves. So the Pauli exclusion principle holds. It's actually a little bit more valid than just atoms, okay? The Pauli exclusion principle in its entirety will actually tell you that no 2 fermions operating under the same potential well can ever have the exact same set of quantum numbers. So you can explain the configuration of the electrons in the periodic table by thinking about the Pauli exclusion principle and then some other rules that guide it. So for example, if you're in the 1s state, that would be n equal to 1, L equal to 0, ML equal to 0, right? And then what you would have is a spin up and a spin down particle that it could exist in that state. So in s orbitals, there can be at most 2 electrons in those s orbitals, right? So lithium, for example, which has 3 electrons, will fill the 1s and then have to put 1 in the 2s, and so on and so forth, okay? Now there's also a rule, I believe it's called Hund's rule, although I'm bad with nouns, that if you have multiple orbitals, so for example a p orbital has L equal to 1, so ML values could be 1, 0, or minus 1, showing the 3 columns here under the 2p. And then each one of those, ML 1, 0, and minus 1, can hold a spin up and a spin down. But Hund's rule states that those electrons prefer to be unpaired, which explains the configuration that you see here for nitrogen. Okay? Okay, now that kind of helps explain the structure of the electrons within an atom. But in order to understand bonding, you have to understand how the electrons in one atom then attach on to electrons in a separate atom. Okay? Now this is fundamentally due to electric forces. And these forces are related to a potential energy function, which is kind of sketched with this solid orange line here. It has this sort of general shape. Now there's different models, including the Leonard-Jones and some others, that explain exactly what function this is, okay? But they all have kind of that same shape to them. First of all, they have this hard wall potential, so that here R is the distance, center to center distance between neighboring atoms, nuclei of neighboring atoms, and of course if R goes to 0, you have fusion. So there's a hard wall repulsion that you would have to overcome, and it would be the energy required for fusion to occur. So of course this is a big cliff right here on the left-hand side. And then it'll go down, and you can see that it's energetically favorable. In other words, there's a potential well right here for bonds to form. The minimum of the function will be the center-to-center distance, or the bond length of the atom, which is the equilibrium separation. Okay? And then as they get further and further apart, of course, the bond becomes weaker and weaker, and so the potential energy approaches 0 as they get further apart. So a stable molecule would be expected at that minimum right there. There's different types of molecular bonds. There's ionic, covalent, metallic, and van der Waals bonding. Ionic bonding is when 2 atoms combine because 1 or more electrons are transferred from one atom to another. This generally happens with atoms that are on opposite sides of the periodic table. For example, the alkalis with the halogens, for example, as is shown here. Here you have a sodium metal ion and a chlorine non-metal ion. They're both unstable. The chlorine's on the far right-hand side in the halogens, and it wants very much to accept that electron. And the sodium is all on the way on the other side, so it very much wants to donate its electron. And then that leaves a net positive charge on the sodium and a negative charge on the chlorine. And because of Coulombic attraction, they stick together. So that's ionic bonding. So as you can see here, here's the periodic table. The way that we use the number that we use to kind of quantify how likely something is to form an ionic versus a covalent bond is called the electronegativity. The stuff on the far left-hand side, as I was saying, those are electropositive elements, and they like to give up electrons. And the stuff that's in this group 7A column, those are the halogens, and they really like to acquire electrons to become negative ions. Of course, the inert or noble gases are in the very last, and they don't really want to bond with anything. They're happy the way they are. Covalent bonds between atoms form when electrons are shared between neighboring atoms, and this happens when atoms have similar electronegativities. What happens then is that wave functions of the two neighboring atoms overlap, and they form a compound wave as shown here. Okay? Now, the number of covalent bonds that's possible for a particular atom is determined by the number of valence electrons. So if you have N prime valence electrons, an atom can covalently bond with at most 8 minus N prime others. So valence is 8, right? And if you look back at the periodic table, if you count 1A, 2A, 3, 4, 5, 6, 7, 8, okay, ignoring the metals here in the middle, then that's the valence, 8. Full is 8, and it's happy. Covalent bonds are directional. They exist between specific atoms and only between those atoms. And so you have, for example, s orbitals overlapping. It's a very directional dependence there. Or s and p orbitals interacting. So it's along the center to center. You can have p orbitals, which make these, of course, figure 8s that connect like that, center to center. Or, and this is fun, you can have p orbitals that are perpendicular to the line connecting the centers of the two atoms, and they overlap like that. Okay, so that's possible too. Here's a chart of the electronegativities. If you need to know this, then of course I would give you the chart. All right. The values of electronegativity range from 0.7 to 4. Smaller electronegativities mean they like to give their electrons up, and larger electronegativities mean they like to accept it. The far left-hand downward side of the periodic table is the lowest electronegativity. That's francium there. And the upper right-hand side, fluorine here, is the highest electronegativity. So it very badly wants to accept electrons. Now, in general, there's not really, something isn't really 100% covalent or ionic, right? Generally, there is some degree of sharing of electrons. A fully ionic would look like this, where all the electrons are just completely donated from one to another. But really what you have for the most part is they still kind of share, right? And then you would have something like a polar covalent bond. So if the electronegativities of the two atoms are greater by an amount of 1.67, then we consider it an ionic bond. And if it's less than 1.67, then the bond is considered to be covalent. And then if it's in between those two values, 0 and 1.67, then the electrons spend more of their time with the more electronegative atom, and that's a polar covalent. Okay? If the difference between the electronegativities is 0, then they really are sharing, and that's nonpolar covalent. So, for example, when carbon forms bonds with other carbons, then that's a perfect covalent bond, and they're really sharing. Metallic bonds. Metallic bonding, the model for that is described in intro physics in the Drude model of conduction, and then refined in quantum mechanics. So the idea here is that one or more electrons is donated from each metal atom, and those electrons become part of what's known as the free electron sea, or the free electron gas. Those electrons roam around the metal and act like a glue that bonds the positive ionic cores that are left behind together. Okay? Now, these are non-directional bonds because the electrons are swimming all around. And this kind of bonding dictates a lot of the properties that you see in metals, like the fact that they're good thermal and electrical conductors. Of course, if you have a lot of free electrons roaming around, it's going to conduct electricity well, right? And since those electrons have a lot of kinetic energy, they also make good thermal conductors. They also act like a cushion, and that means that when the metal's hammered on, the non-directionality of the bonds ensures that the ionic cores can just slip past one another, so you can rearrange the ionic cores, but the sea of electrons keeps the metal intact, and that makes metals malleable and ductile. Van der Waals are the weakest bonds in our laundry list of bonds that we presented earlier. And then among van der Waals bonds, there's subclasses of bonds, okay? So dipole-dipole forces are sometimes called orientation or Keeson forces, and these are forces between molecules that have permanent dipole moments. So these are the strongest kind of van der Waals bonds. They're hydrogen bonds, and they form between molecules that have an NH, OH, or HF group, like water, ammonia, and hydrofluoric acid. They have very large intermolecular forces, and that causes a high surface tension in liquids and high boiling points. Dipole-induced dipole forces are sometimes called inductions or Debye forces. These are weaker than the hydrogen bonds, and they occur when a permanent dipole moment approaches a neutral atom or molecule and tugs at the electric cloud to induce a dipole. Induced dipole or induced dipole are sometimes called dispersion or London dispersion forces, and these are your weakest ones. We talked about different crystal structures that can be formed. We focused on metals because they're easiest to talk about. If you continue on in study of solid state physics, you'll have to, study a lot more of these, but metals are easy to talk about, so we always do them first. They tend to be densely packed because only one element is present, so all the atomic radii are the same, and because metallic bonding is non-directional, and the nearest neighbor distances tend to be small in order to lower that bond energy, and the electron cloud shields cores from one another. So they have all those reasons, they have the simplest crystal structures. So there's 4 that we looked at: simple cubic, face-centered cubic, hexagonal close-packed, and body-centered cubic. A simple cubic is just exactly what it sounds like. It's a cube, and then at each corner of the cube there's an atom, okay? And this is the unit cell, which is the smallest repeat unit of a structure. So the close-packed directions are the cube edges, and the coordination number is 6. That's the number of nearest neighbors that each atom has. There's body-centered cubic, which is a simple cubic with an atom stuck in the middle, okay? The atoms touch each other along the cube diagonals, right? Actually, I should say the simple cubic, there's not very many materials that actually have this packing structure. Only polonium out of all of them has this structure. But for body-centered cubic, there's a number of them. Chromium, tungsten, alpha iron, tantalum, molybdenum, they all have this structure where this atom is shoved in the middle. The coordination number is 8. There's 8 nearest neighbors for each atom. And there's 2 atoms per unit cell, okay? Face-centered cubic, FCC, is a tighter packing structure still. And there's an atom on the cube and then an atom in the middle of each face of the cube. And it looks like this. So some examples of this: aluminum, copper, gold, lead, nickel, platinum, silver. They have more nearest neighbors. You can see its coordination number is 12, and there's 4 atoms per unit cell. So you can see that this would be a tighter, more densely packed structure. Hexagonal close packed is also a tight, densely packed structure. In that one, you have basically a hexagonal structure in alternating layers where the atoms from each layer, they're all in hexagonal structure, but they sit in the divots made by the bottom layer. You can see that here. So it's got an AB stacking sequence. This is what it looks like. The coordination number is 12. There's 6 atoms per unit cell, so it has a very tight packing as well. Now, from these simple structures, you can do things like tug them in different directions and have the unit cell not be symmetric, okay? So the tetragonal, for example, has a square on the bottom, but the distance between layers is longer, okay? And all these angular are 90 degrees. Rhombohedral, it's got a rhombus on the bottom, okay? So the sides are the same, but it's not 90-degree angles between the bottom face. And then you tug it up into the side, okay? Orthorhombic, A, B, and C are the dimensions of your upright solid for your unit cell. None of them are the same, but you've got 90 degrees. Monoclinic, A, B, and C aren't the same, and the angles aren't 90 degrees. And triclinic, A, B, and C aren't the same, and none of the angles are 90 degrees. In monoclinic, one of them, a couple of them are, but one of them's not. You can see there, okay? Okay. Phew! Gibbs free energy. From thermodynamics, the Gibbs free energy is the work needed to create something, or the energy released when something is destroyed. If the Gibbs free energy is less than 0, then the reaction happens spontaneously. And if the Gibbs free energy is greater than 0, then the reaction needs an energy input to make it happen. If we do what we did in our labs and try to use wet chemistry techniques to form nanoparticles or crystals, then what we're assuming is that these things are spontaneously forming in the interior of a liquid. So if you think of that, then you need to think about the volume gives free energy. And this is the free energy difference between the solid and liquid phases in the bulk on a per unit volume basis. This energy will be negative during solidification, right? Because it's happening spontaneously. And the total Gibbs free energy should be proportional to the volume of the material. There's going to be a different energy associated with the surface of the crystal. Surface atoms have a different potential energy than bulk atoms. And in general, the potential energy of surface atoms is higher than that of bulk. And this is often referred to as surface tension or surface energy. It's positive. It takes energy to form a surface, okay? So the total surface free energy should be proportional to the surface area of the crystal. And this is one reason why nanoparticles are different, okay? Smaller particles are going to have more energy than larger particles because of their surface area to volume ratio. Since surface energies are higher, shown here in red, right, and then volume energies are blue, shown in negative, then what's going to happen is it's going to energetically favor forming larger and larger clumps, right, which is why we need capping agents in solution when we did those wet chemistry experiments, for example, with the green tea. The green tea acted as a capping agent, some of them there. So it prevented the nanoparticles from sticking together somewhat. So we talked about capping agents in lab a lot, okay? That stops the growth of the nanoparticle at a desired size, or at least helps it. And when a nanoparticle wants to grow, that's called Ostwald ripening. And if we're going to have nanoparticles remain in a liquid suspension or otherwise come into contact with one another, scientists also will sometimes add a stabilizing agent to keep them from clumping. Lots of times, it's the same chemical that acts as a capping and a stabilizer, okay? So the stabilizing agents and the capping agent work in two ways. They prevent the continued growth of the nanoparticle from solution, that's the capping agent part, and they prevent them from sticking together once the nanoparticles have formed, and that's the stabilizing agent part. In the lectures, we talked about some of the applications of nanoparticles in nanotechnology. One of them that we covered, which is very exciting, is the use of nanotechnology and nanoscience to treat cancer. One of the ways that this can be done is you have a nanoparticle and you tag it with ligands. And ligands like to bind to receptors on cancer cells, some do. And this allows targeted drug delivery or active targeting. Nanoparticles can also passively target cancer cells, even without ligands. And that's using the EPR effect, which is enhanced permeability and retention. Cancer causes tumors, and a lot of those tumor cells act like leaky things. So they have these leaky blood vessels that are grown to feed the growth of the tumor. They're leaky because they're put together so quickly and so randomly, okay? This causes the nanoparticles to move to the tumor cells, but the drainage away from the tumor cell is bad. It's like having a clog in the drain. So stuff gets in, but stuff doesn't get out. So the nanoparticles are going to linger there more than they do in normal tissue, and that's the passive targeting that I'm talking about. Once the nanoparticles are there, they can be used in a lot of different ways. So if you can get them to the site of the tumor, then you can exploit some of their properties. The fluorescent properties can be exploited, and that's good for imaging and diagnosis of cancer. The low melting points can be exploited, making it easy to kill the cancer cells with heat, or their ability to chemical react more actively than a bulk can be exploited by binding them to the cancer cells, causing that targeted drug delivery. Okay, let's talk about nanoscale films for a minute. We talked about self-assembled monolayers, or SAMs, and Langmuir-Blodgett films, or LB films. And these can be created layer by layer to substrates to create nanoscale films. What happens in this kind of film formation is that there's chemisorption or physisorption of what are called head groups onto a substrate of your surface or whatever. And then this chemi or physisorption can become from either a vapor or a liquid phase exposure of the substrate to the solution, okay? Then what happens is, once the head group sticks down, as the molecules start to stick more and more to the substrate, they tend to physically organize their tail groups, okay? So the denser the packing, the more ordered they become. And after some time, they're actually going to form a completely ordered monolayer. And that can be used for chemical functionalization or to lubricate the surface. So selecting the type of head group depends on what application, what substrate you have, for example, that you want to bind the SAM to. Alkane thiols are some of the most commonly used molecules for self-assembled monolayers. They're molecules that have an alkyl chain, which is a long carbon-carbon chain, as their backbone, which is their tail group. And then they often have a sulfur head group that reacts with certain metals like gold. The head groups are going to connect to the molecular chain, and then the terminal end can be functionalized. So you can add a hydroxyl, a methyl, an amine, an acid, or a thiol group. And by changing that tail group, you're varying the wetting and the interfacial properties, the chemical reactivity, that kind of thing. So an appropriate substrate is chosen to react with the head group, and substrates can be planar, like silicon and metals, or curved, like nanoparticles. And finally, we talked about imaging techniques. Resolution of microscopes is proportional to the wavelength of the light or particle used to image. Optical microscopes can therefore not see at the nanoscale because visible light, is 400 to 700 nanometers. So we then turn to other alternative techniques like scanning electron microscopy, transmission electron microscopy, scanning tunneling microscopy, or atomic force microscopy, and they can all be used to image at the nanoscale. Scanning electron microscopy is limited to the spot size of the electron beam. Transmission electron microscopy is limited by the de Broglie wavelength of the electrons, and so it has higher resolution than SEM. In atomic force microscopy, you use a nanoscale tip, which is mounted on a cantilever that moves over a substrate. Either the cantilever deflection for contact mode or the cantilever oscillation amplitude for tapping mode is then maintained and monitored in a feedback loop to generate the image. In scanning tunneling microscopy, you bring a nanoscale tip near a surface, and there's a quantum tunneling current established between the tip and the surface. You apply a bias voltage in between the tip and the surface to make the current move in a preferential direction. And then this tunneling current is maintained in a feedback loop as the tip is scanned across the surface to generate the image. We also talked about other types of characterization techniques in this section, and you should review the basic theory of those. Some of those included quartz crystal microbalances, X-ray diffraction, spectroscopy, and mass spectroscopy. Finally, I'd like to mention that there's labs that we have done that have concepts that I think are fair game for the midterm, and that's because they kind of add on and supplement the lectures in many ways. So first of all, if you remember the agar cube lab, that talked about the surface area to volume ratio and why sort of demonstrated how important the surface area to volume ratio was for chemical reactivities and things like that. And then we did two different labs that had nanoparticle synthesis using wet chemistry techniques. We did a gold nanoparticle and a silver nanoparticle lab. So in both of those labs, we used the idea of a colloid. Remember that colloids are small particles uniformly dispersed in a medium. What we did was we made metal colloids, which are metal nanoparticles in a liquid medium. Now, the way that we made both of these is generally kind of the same idea. We used a metal complex, which is a metal ion in a compound. Specifically, we kind of had metal salts going on for us with the silver nitrate and the gold tetrachloroaurate. So those are our metal complexes. And then we used a reducing agent. A reducing agent is a chemical compound that reduces others by donating electrons to it. And so what happened was the metal complex would break apart in the water, right, that it was in. It would break into the metal ion and the rest of the salt, okay, forming ions. And the reducing agent would donate electrons to the metal in solution, and that would cause the metal ions to then come together to form neutral metal nanoparticle. Okay? Now, to prevent the nanoparticles from growing in size so that they're not nano anymore, we used capping agents. So the capping agent for one of them was green tea or beer or some kind of natural thing, and then the other was the citrate, okay, for the gold nano particle making. And then in the ones that we did, the capping agent was also a stabilizer, and the stabilizer prevented the gold nanoparticles from clumping together, or the silver nanoparticles from clumping together. Of course, over time, the efficacy of that drops and they will clump, and that gives rise to a shelf life for metal colloids. Okay? Then we used different techniques to look at our metal colloids to make sure that we had actually made nanoparticles. So there were two different techniques that we used for that. The first was UV vis spectroscopy, and what that does is it shows that the color changes when a nanoparticle forms, and it actually can give you the wavelength that is preferentially absorbed when the nanoparticle forms. And we did that. The green tea was particularly successful for that. The green tea method for making the silver nanoparticles had that nice peak at about 500 nanometers in the UV vis spectra. And then most recently, we used the transmission electron microscope to look at the metal nanoparticles that we made in the silver and the gold labs. Okay? So those concepts from lab, I think, are pretty fair game there. All right. That concludes the review. I hope you found it useful. And remember that all of these lectures are recorded and the notes are all posted. So if you need to review in more depth a specific concept, feel free to go back and do that. Make sure to look at the homework and make sure that you can do all the homeworks and understand it. And let me know if you have any questions. Thanks.